Day 4 already. Time flies.
Almost there.
So before we break for lunch, we'll take a group picture. We'll have to set up because hopefully we'll make this a recurring event, so you can look how you age as you go through.
Hey boss, when are we stopping?
We're stopping at
Noon.
noon. Oh yeah, ideally, if you want to take a picture, 11:45.
15 minutes. Okay, pop quiz, courtesy of Emily. So, let's ask something we didn't really go over. You have 20 data points and then you're doing bootstrapping, so you like draw with replacement. So why can't we just draw like 50 data points? You have 20 data points, and typically when you bootstrap, you draw samples or the data points again with replacement. So why not just draw like 100 or 50? Or why should we draw 20? Oh, this is too. You know?
Because it's no longer comparable to the original data set then.
Yep. So you did, the actual experiment involved drawing 20 people or 20, whatever you have. And obviously we want bigger sample sizes. And so if we had drawn like 100, our reliability or standard errors would be much tighter. But in reality, we only have 20. So if you're simulating the actual experiment that you did, you have to match it to 20. Okay, what's the most important thing we talked about yesterday? According to me. And then you can answer according to yourself. What did you find most important? Let me remind you the topics we talked about yesterday: bootstrapping, cross-validation, reliability, model accuracy, classification, regression, p-values, group. Actually, we didn't really talk about false positives that much. So what's most important there, according to me?
You said it'll help you reach nirvana if you understand those things.
Regression.
Okay. And what did you find most important? Nate?
Regression.
Oh, okay, great. Obviously. Name one advantage of a randomization procedure to establish p-values over like a parametric test.
Makes no assumptions about the underlying shape of the data.
Right. I mean, that's kind of implicit in the name. I said parametric, so yeah, non-parametric generally means you're not making those, you're not putting parameters and assuming that they actually describe your data. It's relatively assumption-free. If you're resampling data, this is hard. The question is, let me rephrase this question. What's one pitfall of thinking you can bootstrap? Like, can you bootstrap anything? Time points, volumes, subjects, voxels. I see a nod, no. So that's the right answer. Yeah, what would be one pitfall of that? Almost, I wouldn't use the word correlated. The data points should not be dependent on each other. So like, especially if you upsample your data, I mean, you can't imagine you have 1,000 independent voxels, even though you really started off with 2. But even, you know, fMRI data in its raw form is not independent. Like if you were to measure it again, your estimates of error would be overly optimistic if you thought that nearby voxels were actually independent. In one word, what's the point of bootstrapping? Boss.
Statistical underscore testing.
Underscore?
Yeah, you have to have one word.
Oh, actually, yeah, you can use it for null hypothesis test. You can use it for p-value stuff, which we didn't even go over. So that would be a valid answer. I would have said reliability, or putting confidence on your analysis results. All right, one last one. What was the first thing I talked about that undercut the whole lecture? The importance of what? Sorry, I'm not murder model. No, well, I don't remember that, but I started off with visualization, how that's important before you really analyze your data. But you could argue visualization is a type of analysis because you're like, I drew an example of putting vectors. That's like subtracting two data points, and anyway. So, but it still feels like visualization. So that was one of the points I was trying to get across. Okay, everyone passed. Boss gets extra credit for giving an answer we didn't even go over.
Those are the tricky questions. Can you think of the concept I'm thinking of?
Okay, so we have two lectures, although that's a little arbitrary how they're set up. So this first one is on big data issues. In a sense, you've already seen a lot of these issues if you paid attention in the afternoon. So without further ado, big data is not always good. It's only good if you know how to deal with it, I would say. So it's going to make your life painful. So this is a depiction of the rows are voxels, columns are trials. These are the beta weights from a little bit of one subject's data, just for fun. And I'm just using I think I put red to be positive, maybe. Don't worry about the color map. Anyway, this is a depiction of the gigantic matrices that you have. Okay, so there are a number of issues divided by kind of type. So data format issues we've already kind of alluded to. And part of this, I'm going to type into MATLAB. So I'm going to make this window a little smaller. We talked about this a little bit. Let me just give the quick rundown. When you have big data, it actually makes it, you need to think about data format. I mean, if you have small data, everything's double format, which is the default format. Can you read the text? Right, so pi. So that, I mean, you have plenty of digits of precision and, no problem, but it's double format. So I just define A, it's 8 bytes. So 8 bits make a byte, and so now this is 64 bits. So we're using that much storage to store this one number. So that's what double is, and then typical formats are single. So I'll just do this again just in case you forgot. So you can cast this variable to single just by using that. This is a function, I guess. And you can see that it tells you it's single format. Notice we've halved the storage. We talked a little about integer format, so I can cast this to integer now. And now it's effectively an integer, which is no longer pi, and now it's 2 bytes, so we've halved it even further. And then you can you can test for equality on 0, and then pi becomes 1, true. That's kind of a joke. You don't want to do that, but you've further halved your storage requirements. Okay, so no one wants to worry about these issues except that when you have huge data, you have to. Because we've already seen these beta weight files, some of the scripts loaded 2 sessions, let alone 40 sessions, and even the 2 sessions was somewhat painful. And that's already been optimized. Those were saved in integer 16-bit integer. If I had saved it in double, be prepared to wait 4 times as long, or 8 bytes, 2 bytes, it would have scaled by 4. So 5 minutes becomes 20 minutes, or 20 minutes becomes hour and a 20 minutes. So these issues are important to keep in mind if you are going to deal with big data. At least the way MATLAB handles things, to do real arithmetic, you got to do at least single format, which is not really true, because if you really know you only deal with integers, you can do integer arithmetic, but that's rare. So if you're dealing with decimal format, you got to make sure you cast to single at least, if not double. As far as I know, there's not much computational cost to doing things in single versus double. So I guess when memory becomes an issue, you should probably do it in single, unless you're super concerned about precision. So these are kind of hairy issues. Anyway, so like the beta weights were in integer format. The first thing the scripts did was cast it to double, either double or single. I can't remember which script did what. And that's important because otherwise you will get weird things like this. So if you combine this with a actual decimal, it did not work, or it probably did not do what you intended. Let me put it that way. And I don't think today we'll have breakouts, so I need you to pipe up if you are confused. Okay, so when you're computing, you have variables in your workspace. So when you have huge variables, you need to be cognizant of that. In fact, you should like keep in your head like what variables are huge, because it's going to cause headache. So that's for RAM, which we're going to talk about in a second. And then there's disk space. So you also need to be aware of like which aspect of my data set are huge. And from NSD, it's the betas. Like all the other files, I mean, they're big, gigabytes, but they pale in comparison to the beta weights. Like the T1s and the T2s and the ROIs, and that's all like easy stuff. The betas are the elephant. Okay, yeah, and again, data format, when saving to disk, you may want, and this is what I did, I thought about integer and I thought about the scaling factor. That might be okay, 300 was the number I used. So if you have your own data that's big, you may want to think about these issues. Any piping ups? Okay, moving on. Compression. So I don't want to spend too long on this because there are many different file formats. We can talk about text format and all this stuff. But in the context of MATLAB files, at least modern versions of MATLAB, I guess 7.3 or later, you can control what kind of MATLAB version format these mat files are. You can do, in fact, I'll just do it right here. So let's generate some data. Okay, so that's how big is that? 8 megabytes? That's nothing. Let's do that. Okay, that's 80 megabytes, I believe. So when you save a map file, this may be controlled by preferences. You may have to check your preferences, but you can explicitly tell it to save in this particular MATLAB. Let me change my desktop. The 7.3. I don't know what my default is. I should know. Okay, so that took 5 seconds roughly. And so this file is 84 megabytes. So if you can read the help on the save command, but there is a flag that you can use called no compression. And let's just do a comparison. You can kind of look how much faster that was. In fact, I should have done a tick-tock. So now that we're talking about nerdy stuff, we can do stuff like this. So let's do a test 3. So by default, it's saving in compressed format. So it's taking my Gaussianly distributed numbers, which aren't really compressible, and it's spending computational time trying to compress it. And it took almost 6 seconds to save. And then I can do the same with this flag. And then tick-tock it. That's crazy. That's a 20-fold speed up. And if you compare the file sizes, the compressed one was 84 megs. Oh, wow. No compression was actually smaller. Probably there's weird reasons for this. There's like extra header information or something. In general, that's probably not going to happen. This was the worst possible case for compression since they were randomly drawn numbers, right? Other data that have like a lot of zeros or, Anyway, so don't worry about the file size, but just look at the time. There's a time overhead, and it's actually huge. But again, there's computer time and your time. Your time is more valuable. So for the most part, if it takes 6 seconds when you're done with your analysis, who cares, right? So don't worry about these until you have to like spend hours like waiting for it to load. Then you need to worry.
Can you say anything about how this interacts with the space, especially if you're accessing over the network?
That's coming. So NIFTIs, being a little more neuroimaging specific, let's talk about NIFTIs briefly with regard to compression. I mean, typically can you read that? Oh yeah, you can read that. So I'm just gonna pull in some this is an ROI file, I guess it's 0.8 millimeter. That was my convention. So I'm just gonna copy it to my computer just so we get off. Actually, it is my It is on my computer. Anyway, so I have this nifty file, and it's just 700 kilobytes. That's like trivial. But one thing to be aware of, it's gzipped, which is a compression. It's lossless, like it's not like perturbing your data. If you look at what happens when you unzip it, it's 300 megabytes. So we went from 700K, which is like a megabyte, so it exploded by a factor of 300 in terms of space. And the reason is it's largely compressible because it's just an ROI file. And let me just remind you what that looks like. So the moral is that is a compressed format, and there's good reason to do it, especially for ROI files, because no one wants to save an ROI file that's 300 megabytes when you can get by with 1 megabyte. So this is highly compressible. I mean, not that we need to get into the specifics of how compression works, but basically it's largely homogeneous within large chunks of this file. So that's why it's hugely compressible. And that's why it makes a lot of sense to compress those types of files. But other types of data, like fMRI data, become much less compressible. But the default, as far as I've seen, almost no one saves .nii. Almost everyone saves .nii.gz. But it's just something to think about. Oh, and another thing, just to play on this, so we can tick-tock this load. So now I'm going to use this little toolbox that we have used in the scripts. So you can give it a GZ, but under the hood, it's unzipping it. And I can show you the line where it does that. And it's actually sad because that. Okay, it took 9 seconds to do that. And let me just save a different variable. Anyone can guess how long this will take? More than 1 second or less than 1 second? Oh, less than 1 second. So that's a ninefold hit, which is ridiculous. But this is a huge cost, right? You don't want to save a 300 meg file, right? So for ROIs, yeah, it's gzip it. But for other types of files, you may want to consider storing them unzipped. Okay, moving on. Yep. There's no problem other than time. Time is your enemy. In fact, I switched, and this was extremely painful. The betas I saved for the FS average space were, you don't see this, but I saved them, I used to save them in MGZ, which is a gzipped MGH file. And there was a huge cost. So I ended up unzipping all of them and saving them as MGH files, which is actually what you have. And yeah, so there is no problem except that it takes 3 times as long to load. Okay. So there are lots of trade-offs. There's disk space and computational time, and there's your time of worrying about all these things. So you need to just decide what the balance is. And all things considered, I mean, here we're actually getting ahead of ourselves. We're talking about disk space. I mean, there are other things to also worry about, like memory, which we're going to talk about, and network speed and all this stuff. But in general, nowadays, with modern hard drives, you can get like terabytes for like $100, right? So given that money's part of the equation now, disk is cheap, so that changes everything. Back in the day when actually most of you probably don't know, but in the 90s, 600 megabytes was like this big, like a really heavy 10-pound device, like less than a gigabyte of, anyway, and it was expensive. Okay, RAM. So we've already touched on RAM a little bit, but let's address it formally. These iMacs are pretty poor. The one I was on was 8 gigabytes of RAM, I believe. Oh, this is me VPNing into that machine. And I think it's just 8 gigs, and that severely limits everything. So this is 8 gigs, and my local laptop, this little puny MacBook Air, I think it's a little higher, 16. But not that you need to set up your computational stuff like I do, but I don't do any analyses on my laptop, like zilch. Aside from little, tests like this. This is running on my local laptop, this little terminal. So that, I mean, for big data, you can't get by really with 8 gigs. Like your life will be pain. And hopefully you know a little bit of how memory works. At least in the framework of MATLAB, when you launch, you don't have anything in memory. You don't have any data loaded. You got to get data into memory. So then it starts occupying some memory, and then as soon as you compute on it and create like a new variable, that also cranks up the memory usage. And at some point, you'll just run out of space, RAM, if your variables get too big. And then what do you do? Well, you just have to spend time programming a more efficient, in a sense, or an analysis that doesn't actually use that much memory. So what you can do is chunk. So here I just say, well, the basic workflow is you got to get data in, you got to compute on it, and you got to save results. So if the data is too big to load in all at once, you got to do it in chunks. So like subjects, and we've seen examples of that. You for loop over the subjects. There was at no time, I don't think, in any of this. Actually, so some of the scripts did it by subjects. So you load in subject 1, you do the whatever analysis, the t-test, the MVPA, and then you like save the result, and then you like get rid of that variable, and then go to subject 2, the variable that held the data. That's pretty straightforward. I've already done who's tells you what is being used in your workspace. I guess if you have the GUI, it also has that thing on the side. I can launch a GUI if you, oh, there's a GUI on this guy. Yeah, so over here, whoops. Let me just make a big variable. So there, I guess it's convenient because it kind of shows it. Oh, it doesn't show the memory usage though. That's not cool. The memory usage is this thing. Maybe there's a way you can get the GUI to show it. I don't know. Okay, oh, I also have a function to, if you're curious about it, you can look at it. It's not that long. Actually, let me show you like this. It's basically, it calls who's in a function call, I guess, and then does a little math to figure out how much memory is being used. Anyway, so that's within MATLAB. You can check its usage. Another way to do it is check your OS. Like the computer that MATLAB is running on also has, I mean, MATLAB is just one application on your computer, and you have other applications running. So on the Mac, at least, it comes with Activity Monitor, which is a program which itself uses memory, which is kind of ironic. But you can sort by memory usage, which is fine. Or you could also use top. So top is a command line, kind of a Linux or Unix type thing. The Mac is weird. You can't sort by memory. You have to like type top-o mem. And then, yeah, that you see right there. So MATLAB is currently using up 1.8 gigabytes of memory. You can sort by CPU, which would be -o CPU. And then currently I'm not really doing much. Oh, apparently I am doing much. What? Zoom is going, this little PA system is going. Okay, so anyway, you can use top to monitor memory usage, and then I'm sure some of you have heard this. Raise your hand if you know what swap is. Swap, 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 swap. Some people. Swap basically means you have a finite amount of RAM. If applications request more memory and there's no more, your computer could crash if you didn't have swap, like it just can't go anymore, and then it doesn't know what to do, and it'll just either refuse or crash or something. But swap nowadays exists, which means if an application needs memory, and then you have all these other applications that are using the existing memory, the OS is smart enough to know which ones are essentially dormant, but they're not really requesting resources. So their memory usage goes to disk, and that frees up space, RAM, for the guy that wants the memory. But it's very costly, because now you're writing to disk, and then your computer's going to slow down because it's saving files. And so you're wondering, like, why is the computer getting so slow? Well, it's because it's hitting the swap space. So basically, if your analysis starts swapping, chances are it's going to take infinite time to finish. So just kill it. So basically buy lots of RAM if you have money. So get some money. Money does solve some problems. Okay, so let's go on. Oh, so this is a server I have access to. That's 512 gigabytes of memory. So that's good. 512 is much bigger than 8. Oh, that's just top. So if you look at top, it's in the upper left corner. But you have to like do the comma to figure out what it's actually saying. But that's 512 gigabytes, or yeah, well, 529 maybe, depending on how you count. Okay, disk space. As I said, like disk space is fairly cheap. So if you have funds and you want to sketch out a system, don't skimp on disk space. There are different types of hard drives, not that we need to get into those details, basically solid state drives versus traditional magnetic platter drives. Magnetic platter drives are cheaper, but slower. Solid state is super fast, but expensive. So you got to make some choices there as to what you need. Yeah, so now you're trading off money for speed of loading. So if you're willing to spend a lot of money, you can do analyses really quickly. Sorry, you can do loading of data really quickly. So sometimes you have like a solid state drive and then a huge RAID, or like traditionally like a magnetic platter drives, HDDs, I guess. But if you have a solid state drive, you can do things like store your OS on it, because your OS is going to constantly access all of its system files. You might want to store your code on solid state so that you can just load it super fast, that you can refresh your path really fast, like things like that. Or like NSD, one of the directories of NSD data is like not the beta weights, so it's relatively small. So you might consider sticking that on solid state just so you have super fast access to that. Obviously, going to disk is painful, right? In the case of swap, it's very painful. But in the case of like data analysis, just loading the data, as you saw yesterday, it's painful. You have to sit there and wait. So you want to minimize it. And what that means is, it's probably obvious, but like, you don't want to save results immediately. You do some computation. If you save, I guess you save to not lose it maybe, but on the other hand, it takes a lot of time. So you want to like do a significant amount of computation and then maybe save at the end, if it's big data. If it's small data, then none of this matters. Oh, and file format / organization. For various reasons, it's expensive to store data in a lot of files. I actually don't know the low-level reasons for that. Basically accessing in one file at a time has some overhead. So if you have 1,000 files, it's not going to be good. So for example, the NSD stimuli, if you remember 3 days ago, whenever it was, we ended up storing them in HDF5, which means 73,000 images are in one file. And that means if you have 40 gigabytes of memory or more, you can load that file as fast as humanly possible, or computer-wise possible. But if you split that up into 73,000 files, we could do a little speed test. It would be slow as molasses. But then there's this other issue of random access. Hopefully you remember this HDF5 format thing. If you store in many individual files, that makes random access easy, because you just get that file name and load it. Whereas if you we can also do that with HDF5, right? Because it is designed for that. We could pick out one image very quickly, and we did that in one of the scripts, hopefully you remember. But that's because we use HDF5. But if you did something like gzip, if you did the dumbest thing, which was like make 73,000 images, PNG files, and then gzip the whole thing, your life would be hell, really. You would have to unzip the gigantic thing. Anyway. So strategies, well, load what you need. So if you don't need all of the voxels, only load the one voxel you need, or the 10. Or if you don't need all the subjects, load one subject. So in MATLAB, hopefully you know the syntax. You can load, if the mat file contains many variables, you can load one only, and it's fast. So whoever designed the implementation of the mat format made it such that you can random access individual variables from a file. So you can have a map file that's like 10 gigabytes, but if you really just need like one little tiny vector from it, you can get it extremely fast just by knowing what the variable name is. Oh, right, HDF. So we talked a little bit about HDF5 format, and that allows random access. Let me stop for 10 seconds while you think of questions. Yep. Is what?
So if you have a solid state.
Oh, yep. You could, if, for sure. Yeah, so if you know what you're doing, you can put your swap on a SSD drive, and then the hit for going to swap isn't as bad as HDD. But I think solid state is still, I mean, RAM is much faster than any of this, but any other? Yep.
I don't know if this is going to go off topic at all. Can you talk a little bit about parallelization in MATLAB?
Yeah, I have a bullet point, but yeah, we can expand on that once we get there. Yeah, I didn't know, I mean, we could go in more detail on any of these points, but yeah, remind me about that. So that's me when stuff takes too long. So this is, we're not talking about loading from this. We're not talking about RAM being not enough. We're just talking about, you know, multiplying matrices when everything's already loaded in, and, you know, stuff takes time. Multi-threading basically means computers nowadays have many cores. So even my laptop has 2 cores. I don't know how many the iMac has. Oh, iMac has 4. Cool. Series workstations can have like 16 or 32. And what that means is they kind of behave as independent CPU things that can manipulate, do computation. And in most of the basic fundamental operations MATLAB are multi-threaded. So in other words, you don't have to do anything special. It automatically uses all the cores that it can get from the OS. And you can see that by doing top or activity monitor. I can probably do that here. So if I monitor the CPU usage, Zoom is eating up a lot. And so maybe I'll do it on this screen sharing thing. So now I'm on an iMac. And activity monitor. And then let's make some big variables. I can make this bigger maybe. Anyone know how to make this bigger? Font size. I'm not doing anything interesting. I'm just going to make 2 huge matrices, A and B, and I'm going to multiply one times the other. Oh, that's too fast. So I'm just going to put this in a gigantic for loop. Here we go. Okay, it's just doing that 100 times. I'm just showing you. You can monitor the CPU. Oh, there you go. Look, it's already at 400. Yay. So we're using all 4 cores. Activity. I don't like activity monitor. It's slow. You can just use top. So remember, top-O CPU. Oh, it's done already. Got to do it again. Come on. Uh-oh. There's somewhat, sorry. There's some quirk in there. Oh, there we go. So here you see it's 369, 377. That's good. But you will find sometimes that some random piece of code, for various reasons, is not multi-threaded and it'll max out at 100. Then you're sad. FreeSurfer is like that. There's some command in FreeSurfer that it'll just go to 100 and it's just slow. But that means you can process many subjects at once. Just open up 10 terminals, launch your recon all, and then watch the 100% go. All right. So how do we deal with analyses taking too long? I guess in the scripts thus far, it hasn't really been that much of an issue. It's been the load that's been painful. Maybe the MVPA script was somewhat heavy. I mean, I sped it up by, you're only doing searchlights within that little ventral mask. So if you did a whole brain, you would be sitting there for maybe 10 minutes. Okay, so how can we deal with this? Well, that was just one subject, of course. If you did searchlight one subject and you have many subjects to do, so opening multiple sessions is only going to help you if each individual session is not multi-threaded. So for the most part, things are multi-threaded, so probably this is not good for that, except for that freezer, for example. I mean, there, it's not multi-threaded, so if you have lots of subjects to process, you can speed things up just by doing things in parallel, even on the same machine. Of course, if you have access to multiple machines, you can parallelize that way. Just SSH into each machine, which is kind of annoying, launch whatever you're doing, and then all the machines will be working. Parallel commuting. Wait, is this what you were? Yeah. So parallel commuting, what do you want to know? Yeah, so I mean, the basic is, it is a very MATLAB specific thing, and different software, different programming languages will handle it differently, but within one MATLAB session, if you explicitly ask for parallel computing, so it's called the parallel computing toolbox. Par4 is the command, so instead of a for loop, you would type par4 and then the very similar syntax. So what that does is, traditionally a for loop is one at a time. For p equals 1 to 10, do that, then do that, then do that, do that. Par4 tries to do all of many at the same time, where you can get up to the number of workers, they call it, but it's limited by the number of cores on your computer. It's also limited by how many MATLAB allows you to do. I don't know why they put limits, but typically you can get like 4. I mean, you can request whatever you want. You can max it at 4 if you have 4 cores, or 8 or 12. I think I've seen 16 even, or even 32 maybe. I don't know. You'd have to check whatever version you're using. But let's say you do have 32 cores, and let's say you can request 32 workers. Then if you have the contents of for loop, let's say it was single threaded for whatever reason, you can do 32 simultaneous iterations of that for loop at the same time. So you can get a 32x speed up, theoretically. So if you're doing like searchlight, you can get it done 32 times faster if it was not multi-threaded. If the stuff inside is multi-threaded, it's not, I'm fairly certain it's not going to give you any benefit. So par4, I kind of don't use it that much because for the most part, I'm happy to use the multi-threaded capability of most low-level code. Occasionally I do use it when it is in fact, yeah. Anyway, I sometimes use it. It comes at a cost, and this is MATLAB specific. The syntax of your for loop has to be very specific. And I don't have it. I think we should, it's not really something I think most people would be interested, but we could, if you had a specific piece of code, we could want a par4, we could look at it. Yeah, I don't know. We can talk more if you're curious. Okay, another option is cluster computing. You guys have a cluster, right? Boss? Like many boxes with many cores each, that type of thing. Yes. That are all on a common network. Okay, so that's definitely an option, but there's significant overhead, so you have to figure out how to use it. And not only that, you have to like structure the code and your files very carefully in order to make it worth your while. Like the same issues we've been talking about. Loading from disk can be a gigantic pain if you have 50 computers trying to load significant amounts of data at the same time. So you have to carefully craft your data and code before you can even reap the benefits of going to a cluster. And then there's like overhead of just the scheduling system. You have to like format your analyses into little jobs, figure out how to submit jobs, monitor your jobs. If they crash, you have to like resubmit them. It can be a lot of pain, but if you have to bite the bullet, maybe. So if you want to bite the bullet, there's significant overhead. It will cost you time, but if you get to the point where you can use it well, it will, you know, I once had like 1,000 jobs going at the same time. So that's, you know, theoretically 1,000x speed up. So analysis that would have taken, you know, 1,000 hours now takes 1 hour. GPU computing, that's pretty niche, but it is a thing. GPUs are a special type of chip. Not all computers have them. If you have them, they're very good at certain parallelizable operations that don't actually use a lot of memory. So, and then you have to specifically code for those chips. So there is overhead on your part doing that, but it is an option. Maybe the easiest option is just write good code, like bread and butter, standard MATLAB code or Python code, whatever. And I'll talk about that in a minute, I think. Oh, profiler. Let's do some profiler. Anyone that has heard of the profiler? Nobody? One person? Wow, okay. Let's do it. So let's see. I'm on my local computer now. And let's just clear all. And then it turns out I can run these little examples on my laptop. It's cool. And I mean, this is beyond useful. And what I hear is like Python doesn't have equivalent. So I just did help profile. And then what I'm going to do is profile on. I'm just following this example. Then I'm going to compute a bunch of stuff. No, I'm not going to do that. And then at the end, you just like do this funny little command. Okay, so this prof save thing. So right now there's like a little daemon monitoring my code running. All right, so let's go. We'll just do example, I don't know, example 6. Example 06. Okay. So it's going and doing stuff. We won't watch it. And so the code is running, and it, as far as I know, doesn't really interfere with what the code does. Like you will get the right answer, but it will slow down a little bit because there's some monitoring going on. And what it's going to tell us is everything we ever wanted to know about computational time costs. It doesn't tell us about memory usage, I think, which is something I was thinking about the other day. Which is unfortunate, but oh, it's almost done. Okay, so the goal of this tool is diagnostics. Okay, it's done, and I got some figures. So it's the fact that I'm idling right now is not a big deal. It's not like that doesn't contribute to the thing that it's monitoring. So it only counts like cycles, actual work. So it's done, and then I could run more commands if I wanted to, I guess, but I'm just curious about what has happened thus far. So I'm just going to run that. And this is somehow accessing some files it saved in the background or something, and it's going to prepare it nicely soon. Yeah, we'll talk about that in a second. Come on. Okay, I'm impatient. Let's talk about the next thing and we'll go back. So vectorization, have you heard of that? Raise your hand. More signs of recognition, good. Basically, it means like avoiding iterative computation like for loops. So for loops means do this, then this, and this. If there's some way you can do the entire thing at once, then that saves you time. Actually, I would type it out, but I actually was playing with this a second ago. So here's my little example. Correlation, everyone's favorite. So I'm going to have 100 voxels and they have 10,000 trials. And then I'll have some other thing exactly the same size or something. And I want to correlate each row with each other row. So like, I'm drawing a blank. I don't know when you would do this, but I'm sure you could do this. Anyway, so here's one way to do it. So this is the naive way. So let's loop over voxels. So I'm going to pre-allocate this little result vector 100 by 1. So every voxel is going to get a correlation value. And I'm going to time this with tick-tock. And I'm just going to loop for each. Oh, shoot. This one was actually the other way. Wait, is this right? 100. No, sorry. The interpretation is 10,000 voxels and 100 time points or something. I should have commented this. Okay, so I made the numbers big to make it really bad. So here we go. So wait, am I doing this wrong? My brain's not working. I'm correlating each column with the corresponding column from the other matrix. Right, okay. So I should have pre-allocated like this. Okay, anyway. I think my other command ran. We'll revisit that in a second. Okay, so this took, oh, that wasn't that bad. Let's make it harder. Wait, am I swapping? Is that why it's taking forever? Oh, sorry. Someone should fix my bugs here. I'm not even indexing correctly. Okay, that was too long. We need the porridge to be just right. Come on, porridge. Anyway, okay, so this is the slow way. This is a for loop method, and core is a built-in MATLAB from the stats toolbox to do Pearson's correlation, and it took 8 seconds. And if all you had access was to core unfortunately works on one vector, like pairs of vectors at a time. Like if you're, a scatter plot, you commute a correlation between x and y, you feed it x and y, and these have to be vectors. So here, I'm just using my implementation of the operation. About 6 times faster. So, I mean, the one here was my way of indicating I want to compute the correlations column-wise to match what we did up here, but that doesn't matter. The point was, if you do a for loop, it can be very slow, but if you recode this whole thing in a vectorized format, it can be very fast. As for what that means, essentially, well, it kind of means avoid a for loop, but what that also means is somehow compute Pearson's correlation for all voxels simultaneously. So we didn't even talk about what correlation is, but I'll give you an intuition. To compute correlation, you have to first subtract the mean from each thing, like each voxel's time series or something. So that's one thing you got to do. You also have to scale it. So if one version of correlation is like you essentially z-score the things that you're correlating. Z-scoring means subtract the mean divided by standard deviation. So you have to subtract the mean and somehow scale it appropriately. And then you compute the dot product of the two things that you're correlating. So a dot product, which we didn't even talk about, you have two vectors, you pointwise multiply them and sum. That's what the dot product is. And the dot product can be achieved through a matrix multiply. Hopefully this rings the bell for some of you. Anyway, so you have to subtract the mean, you have to scale, and you have to essentially matrix multiply. And if you think about it, all of those operations can be done on at the matrix level, if you do it right.
That's the tricky point. Right? It's easy to say, oh, you should vectorize your data. It's much harder to say, can you show what's in the calculation?
Okay, here you go. So we're computing, let me just make sure, columns. So we're recording each column of A with corresponding column from B. So for A, we got to subtract the mean of each column, I believe. So let's just do it kind of as clearly as possible. So this operation is vectorized. I mean, I didn't type a for loop. We can take the mean of each column. And I guess if we were curious why what? Wait, what the heck is going on? Sorry, this is some obscure it's actually showing me the documentation of a different function called mean, not the built-in mean. That's very odd. I'm sort of curious. Let me, I'm just going to cd to the MATLAB file called mean. Okay, this is MATLAB's version. Oh my God. It's agreed to take this at face value that mean is somehow vectorizable. There's no for loop in here, but there's a lot of stuff. What about sum? Oh, sum is built in. Sweet. So here, I won't use mean. I'll calculate mean by hand. How about that? Sorry. Yeah, right. I'll sum each column and then divide by the number of elements. Happy? Okay. A sum is this, and this is fast. And sum is a built-in function. We don't even see its implementation. It's some compiled assembly code or something. Okay, so we avoided for loops. Great. So how do we compute the mean? We scale it. I'll just do it in one line. Scale by the number of elements along the first dimension. Good? Okay. So I can get the mean of each column. Now I need to subtract it from all of the numbers in that column, in its corresponding column, right? Okay, so let's just, I'll make a temporary, A temp is just the original A, and we want to do something like that. Nowadays, MATLAB automatically rep maps. Hopefully you know what I mean. Like, the mean we calculated is a vector, but the data is this 100 by 1,000. So we need to like repeat the mean we calculated to fill the 100 rows. And for some reason nowadays, you can just type what I just typed and it will work. But I don't have the latest. Oh, okay. So I do have a version that now, but in old versions it would crash because your two matrices you're subtracting are not the same size. But here it magically behind the scene did rep map, which I don't like because it can cause, you know, unwanted confusion. So this is ugly, but this is what you in the past would have done. So you would repeat that mean vector 100 times, and then you can do the subtraction. Okay, so this is still counts as vectorized because I'm not for looping. So now I have a mean subtracted A. Okay, let me just speed this up. We want to essentially divide by the standard deviation. So to do that, you can say standard deviation along the first dimension. I don't want to unpack standard deviation, right? Okay, good. So now I'll divide by the standard deviation. So I will divide, I got to do the same old thing. I got to rep map this thing. Okay, A temp is ready to go. This is not good coding, but I want to repeat this for B. Wow. Okay, so now B temp is ready to go. And then the last is, okay, let me just remind you what's going on. So all I've done is z-scored each column of A and B. Okay, and then the last step is to compute the dot product, I think. No, there's a scaling involved too. It's not going to be exactly right, but just take my word for it. It's basically what you would need to do. Okay, so now we want to compute the dot product of each column of A with its corresponding column from B. And so the goal is, how do we do that efficiently? Yep. Overriding the results of what? Oh yeah, sorry, I meant A temp here. Yeah, good catch. Okay. All right, so dot is a function in MATLAB, and we could look, if you don't, how does it do it? Oh yeah, okay, there you go. So the dot product is matrix multiplication, right? If you know what's going on here. But all we have to do is say dot along the first dimension, and then we're done. Our result. But nowhere did we have to do any for looping. I don't know if that was like it satisfied your needs, but
Yeah, it's an illustration of how to do it. I mean, this is vectorizing something that I think you can never, well, it's hard to do. Easy to begin, hard to master. as you write code, it becomes clear eventually that most of the things that you're doing when you have a for loop, you can vectorize them. But like figuring out how to do that, you're not always going to be able to sit down and say, okay, now I want to vectorize this part of code. Like sometimes it will just come to you later. It's okay to write it slow first. And then once you go through optimizing, I guess this is what the profiler is going to come to as well. If there's parts that are taking a long time, those are the ones that you might want to spend some time on trying to figure out how to do that.
Yep. So let's go back to the profiler. So just reminding what we did, we started with a blank slate, we turned on the profiler, we ran example number 6, and then I issued that funny command that for some reason took a while. And what it does is it brings up a web page. So on the left are like different functions, essentially, that were called in the process of doing example 6. This is how many times that function was called. So calling functions is expensive. This scatter was called 200 times. Really? Oh, right, yeah. Let's remind ourselves what the figures were. So stupidly, I wrote this figure generation code to plot each dot separately, I think. But, you know, in the end, it took 3 seconds out of the total 36. So anyway, so this is the number of calls. And this column is how expensive it was. I mean, it's pretty self-explanatory. Total times and then self. Yeah, so total time means, I mean, code is hierarchical. Total is like the total time for that thing, but self time is like, if this thing calls other things, that's not it. Those are like their problems. But self is like what is intrinsic to the thing that we're talking about. So this script. So even though it took 36 seconds in total, it itself only took 2 seconds. The rest of the time was, you know, soaked up by the things it used. Okay, and then lastly, there's this probably most useful thing, the graphical depiction of stuff. So dark band is self time. So you want to make the dark blue go down because you're impatient. So who's the culprit here? So I scroll through this gigantic web page. Look at this. This is like nothing. 1 millisecond. None of this matters. Aha! Look at that black bar. Aha! It's the H5 read. So as soon as I see that, I know, don't even go there. Like, you're not going to optimize that low-level routine. So that is like, oh well. But that makes you think like, oh, should I like get a faster hard drive, or should I save in a different format? That type of thing. But if this line was big and was like a function I wrote, then I would know that's inefficient code. Let's spend some time to think about, is there a way to speed up that line? So unfortunately, this wasn't a great example to do because my code is so efficient, there's not much to do. Yeah, that was anticlimactic. But in the background, maybe I'll do some other random script. Let's do the MVPA one. So I just type profile on, and I'll just let it run. Actually, let me clear all first to make it safe. All right, and then example. Whoops. Oh, yeah, sorry, that one. Okay, it's running. And as we've talked about a little bit, like, as Boss just said, like, yeah, if you don't understand how to vectorize it, if it doesn't come firsthand to you or first nature to you, don't worry about it, because especially if you like analyze behavioral data, it won't matter. It'll be just so fast. But once stuff starts taking forever, then you can be like, maybe I should spend an hour trying to think about this. So don't optimize until it becomes painful. Okay, network stuff. So we've already experienced this. Loading those MGZ files or the betas has taken time on these machines. It hasn't been that bad because I set up the script to by default just analyze like 2 sessions, but you know, crank that number to 40 and it starts becoming painful. The data here live on some server somewhere in a different building. I don't know where it is. I don't know the nature of the device either. It's probably HDD. And it's coming to you via cables in the wall, Ethernet. Ethernet nowadays can be up to gigabit. So right now my computer's on 1,000 base T, so that's gigabit. So that's pretty good. And you don't want to be on 100 base T because that's like maximum 8 megabytes a second, but this is like up to 80 megabytes a second. So certainly that could be a bottleneck. Here, I actually don't know if it was the bottleneck. We would have to do some tests. Like, is it just the cost of reading the data off the spindles, or was it the cost of shipping it over to this iMac? We would have to do some tests. But it can very well be the bottleneck. And there's no real solution here because, I mean, unless you have, I don't even know if these machines support more than gigabit. So you're kind of stuck if you have a network set up. The alternative is just compute on the machine that is directly connected to the hard drive. And so that can actually mean different things. That could mean, let's say you only want to analyze the FS average betas. Like, screw the other versions of the betas, the 1 millimeter, the 1.8 millimeter, you don't need any of that. That means maybe you should just copy those FS average things over to the local computer. And that'll take, an hour or half an hour, but that's just once. And then once you've done that, now you have free reign to quickly load from the local hard drive. So that's one route. The other route is just go commandeer whatever machine has these files and just run computations on that computer. Or like buy a huge workstation and then just do all your analyses on that workstation with its own hard drive, which has all the data. And that's typically what we do. It's still going. Oh, this is going to take a while. Yeah, I should have reduced the number of. So in terms of network, I was going to do a little. I was actually just curious, and let's see how long. So I want to isolate what the problem is. So here I have one file. This is about half a gigabyte, so 500 megs. I'm on the iMac, and I'm loading in. I haven't run this command. Let's try it. Oh, I can't even. Whoops. So I do a TikTok. I'm just testing how long does it take to load. Let's pick some. Funny things can happen, like hard drives cache, and like, so cache meaning like they save recently read stuff so that it may look faster than it actually is. So I just want to avoid any of those funny things. I'm just going to pick session 26. Also, other confounds, like this script is running, so it's actually accessing the server, and like other people might be accessing the server, so it's not a super well-controlled experiment. But okay, I loaded from this iMac to the server. It took 8 seconds to load this MGH file. And I specifically chose that, like gzip is yet another aspect. Like if it was gzipped, it would actually involve unzipping to the local computer, and like those are factors I don't want to care about. So I just wanted the raw binary file, no uncompression stuff. So it took 8 seconds, and I guess, oh yeah, we should actually just copy that locally. Is that a fair comparison? So that was from the server going through the network to this iMac. I guess we could compare what if it was local on the iMac. That'd be a good comparison. But I wonder if I can just copy by dragging. Anyone know if that worked? Oh, look, it worked. Okay, so all I did was I copied it to the desktop. Okay, it went from 7.9 to 2.8. So, ballpark, a little over doubling or halving of speed time. So that suggests the network is not the, I mean, it's a major part of it, but not the only part, of course. Okay. Right, so that was an example of this, what I just mentioned. You could just copy once locally, and then you've doubled your speed, just in terms of load. Oh yeah, rack mount servers, buy them. I mean, I assume that's what your cluster is. But are you allowed to just directly run stuff interactively on the cluster? Yeah, log in and open up a MATLAB or whatever. Mm. Yeah, I see. You might have to fight the power. Okay, one last slide of this lecture, and then we'll take a little break. We saw some of this test code on small data. So these little example scripts, let's say they were actual analyses I was interested in. I designed them just to load a few sessions at a time, and they may not be as clean results as if you would get if you loaded all the data, but for purposes of development, there's no reason to analyze all the data. You're like tweaking code, you're generating good visualization. So that's an obvious strategy that you can do to save painfulness. You also saw this in the scripts. To some extent, if possible, can you separate the loading of data from analysis? Because the idea is loading is expensive with big data, but once you have it in your memory, then you can do the creative work of designing your analysis, and you don't have to load it again. It's always in your workspace. Don't like clear the variable or mangle it, just keep it there. And then you can code and experiment with analyses. And that's exactly what the scripts were designed like. So for example, so in the t-test script, I mean, basically, it did go one subject at a time, but when I was developing the script, I spent a few minutes just writing the load part, not even worrying about how I was going to analyze it. So I wrote this little part, and then I interactively loaded it, one subject, and then I kept it in memory and started developing the rest of it, right? So just clearly segregating your code into load and analysis will save your headache, because you never want to load again and load and load and load. Caching things that are expensive. So cache means like save temporarily, maybe. So an example of this would be the searchlight stuff. So I actually don't know if it took a long time to rotate the sphere and like chop off the top of it and find the vertices. So maybe it doesn't take that much time, but let's say it took a long time to do that. If you think you're going to do that operation a lot, there's no reason to repeat it for every time you run a searchlight. Just like save those little vertices that it found, right? Especially with the FS average surface, just that will never change. And if you might have to save 3 versions. Maybe you wanted to do a searchlight that's 3 millimeter radius, 4 millimeter, 5 millimeter. So okay, go off and write some code, loop over 3, 4, 5, save out the results once and for all, and then that'll speed things up, because now you can just, instead of so now we're talking about load time versus compute time. So if you cache, it's going to take some load time to get the results. So you take a hit. So you have to weigh that against how long did it take to compute it. So let's say the compute time was like 3 minutes. The load time will probably be like a second. So 3 minutes versus a second, the advantage is clear, cache it. Of course, the flip can occur. If computing it takes 3 minutes, but it's so huge that it's like a 40 gigabyte file, the load might be longer than 3 minutes. So that in that case, don't cache it. You're going to do worse. You might as well compute it every time. So again, these are headaches that you just have to, it'll become natural if you do it a lot, just thinking about these things. But caching is a strategy at your disposal. You can even think of pre-processing as caching. So fMRI data are huge, you have to do your motion correction and all that crap. And we save it. We save out the result because we never want to go back and do it again, right? So that's like caching it. Yeah, this is maybe obvious. So these example scripts were already done and they ran, but getting to the point of a working script can take a long time. So big data just makes everything harder and harder. Because if you want to rerun the script, it might take a couple minutes to see if it works. And that's a couple minutes of lost time. So you can check your email or something, but the round trip between develop and test just becomes longer and longer. So to deal with big data, you have to like become really good at efficiency, like coding, knowing all these trade-offs of disk space and network and all that stuff. Oh, and that's an icon of someone that's like free solo. So it's like if you make a mistake and launch a computationally expensive analysis and come back 3 days later and realize you screwed up, that's like falling off the cliff. Okay, let's take, we'll come back at 20 after. We're back. Script number 8 finished on the profiler, as you can see here. Really all I look for are the blue bars. Well, and the calls. This is crazy. 118,000 times it called unique. So what that means is the core functions that are used in the type of analyses we do need to be super efficient. Because like, you know, that many calls, I guess in total it took 31 seconds. So just 10% speed up can save, well, for larger scale analyses, a lot. So anyway, so if you ever write functions that you reuse again and again, they had better be good and fast if you care about your time or the computer time. Anyway, so the blue bars, oh, lo and behold, it's the load that's the culprit. So load MGH is some little utility from FreeServe for people. It loads their funny file format. So let me actually click on it because this is what you would typically do. So you get yet another page and it gives you lots of interesting information. Tells you who called it. Tells you the culprit lines of code. And unfortunately, like the previous example, if you know what this function is, it's a low-level routine. You're not going to speed this up. So 98% of this function's time was spent on this line, and this line uses fread, and that thing you're not going to optimize unless you have the chops to do it. But you probably not. Probably you will not do that. Probably the most time-consuming part of this was actually asking the hard drive, give me bits, and that's beyond what we can do. It tells you some other lines, but like the philosophy is like go where it hurts. 0.6% of this function was involved for this. Like, not that you would speed this up, but basically you go look at what takes the most time and think about whether you have the ability to speed it up. If you do, great. Otherwise, all the little things don't matter. And this is just that concept of self-time. So this function did call these little, they call them children, but it's things that this function calls, other functions. It tells you, how many times it called them, but like they are trivial. And in fact, most of the time spent in load MGH was the intrinsic to itself, the self-time. And it was all because of reading from disk. Anyway, and then this other stuff, oh, it's just like comments. Like, your code is not great. Oh, and then, one last thing. At the bottom, there's a graphical depiction of computational time. So this number is like seconds in red. Basically, it'll highlight slow lines. There you go. So it zooms you in onto the culprit. And everything else is petty change. Anyway, maybe let's look in classify. So classify was the machine learning classifier routine that we used from MATLAB Stats Toolbox. So we can actually look at what was, of the, it pales compared to load time, but after load time, can you further speed it up? You can look at the lines that cost. And then it calls some very basic routines like standard deviation. And you can look at how much time they took. Mean was called 118,000 times. Good things that it's pretty fast. So anyway, any questions before we move on?